Hey everyone, it's Justin again. So far, we've learned about multiple methods to solve systems. Elimination is a tricky one because it requires a lot of algebraic manipulation. In this video, you're going to learn to recognize those manipulations and why they work the way they do. We'll be using graphs to make things more clear, so have some graph paper handy for taking notes. First, let's take a look at something we already know. Manipulating a single equation on its own doesn't change the line that it creates. We learned this from back when we learned to change between linear forms, but it goes even further than that. If we take the equation y minus 3 equals 2x minus 1, we can distribute, but the graph remains exactly the same. Then we could add 3 to both sides, which would put it into slope-intercept form, but again, the graph doesn't change. This is why we're allowed to simplify and move pieces around when we're preparing for elimination. Even though it looks like the second equation changed, all we did was change the form it was in, which means the graph didn't change at all. It's still the same system with the same solution. We just made it look a little different so that eliminating a variable becomes a little easier. This is what's known as an equivalent system, a system with the same exact solution, usually because the original equations were manipulated in some way. For this same reason, when we use multiplication to make terms that will eliminate, we create equivalent systems. For instance, this system can't eliminate yet, but if we multiply the bottom equation by 3, now we've got a system where the y terms eliminate. But did we actually change the system? If we compare the graphs, we see that the system is made of the same exact line still, with the same solution. So we didn't really change anything except how the equations look. So now we know that manipulating only one equation doesn't actually change the lines, but what about when we combine the equations? This doesn't just combine two equations into one. It gave us a third equation that fits our system. Notice how the new purple line goes through the same solution as the other two. What this means is that we can create an equivalent system using any two of these equations. We can create a system with the first and the third equations, or a system with the second and the third equations, or all three systems are equivalent because they all have the same solution. So combining equations in a system doesn't just create a new equation, it creates a new equation that can be used in equivalent systems. Combining for a new equation works even without eliminating. Take the system, for instance. If we combine these together, we get this equation. Nothing was eliminated, but it still has the same solution, and it can still be used to create an equivalent system, along with the first equation or with the second equation. All three of these systems have the same solution and are equivalent because one of the equations came from combining the other two. So how can we create equivalent systems? By manipulating the terms in an equation, like changing the form, by multiplying an equation by a constant value, like we do when we're preparing for elimination, or by combining two equations together to create a third equation, whether it resulted in a term being eliminated or not. So let's get some practice. What would we have to do to create this equivalent system? Notice that the second equation remained the same, so somehow the first equation was changed. Were the terms moved around? No, the x, y equals and constant are still in the same order for both equations. Did we multiply the first equation by some value? We could multiply by 1/3 to change the 3 to a 1, but that would also change the 4 to a 1 or the 7 to a 12. So there's only one option left. What happens if we combine the original equations together? Well, we get the equation that replaced the first one of the equivalent system. So that's what happened. We combined the original two equations and then replaced the first equation with a new one. How could we create this equivalent system? Did we rearrange the terms? In the original first equation, the x was isolated, but in the equivalent system, x and y are on the same side. So yes, the terms were manipulated. However, if we manipulate the terms, we would end up with this new equation on top. Clearly, something else happened after we manipulated the terms. Can you recognize what happened? The first equation was multiplied by 2. So this one actually took 2 steps. When you use the elimination method, it looks like you're changing the system with each step, but you're actually just creating a sequence of equivalent systems that all have the same solution. In the final video for this lesson, we're going to put everything together and use the elimination method to solve systems from beginning to end. See you then.